Marhaba. Okay, in this session we want to talk about how can we obtain new relations from previous relations. Okay, so let me elaborate on this idea. We want to learn 4 ways to obtain new relations. Okay, let's introduce the first one. So suppose we are given relations, okay, R and S from, so these are 2 relations R and S from a set A to a set B. Okay, what does this mean? It means by definition of a relation, R is a subset of the Cartesian product and S is also another subset, okay, of the Cartesian product A cross B. So we have 2 sets R and S whose elements are pairs from A cross B. Okay, now we can define a new relation. Okay, so this is define a new relation U, where U is the relation obtained by taking the union of R union S. Okay, so this is the union relation. What is this? Now, how can we think of this? Suppose small a, so what is U? It's the set of all pairs which are in R or in S. So this means an element A in A is related by U to an element B in B if and only if either A is related to B by R or A is related to B by S, right? So this means, okay, so this means that the pair AB belongs to the new relation U. So notice that U is still a relation because it's a subset of A cross B. Okay, since R is a subset of A cross B, S is a subset of A cross B, their union is also a subset of A cross B, so this U is a relation. And it means that the pair AB belongs to this set U if and only if either the pair AB belongs to the set R, the relation R, or the pair AB belongs to the relation S. Okay, now what can you tell about the matrix representing U, which is R union S? How can you obtain this matrix of R union S in terms of MR, the matrix representing MR, and the matrix representing MS? Okay, so remember the entry here should be 1 if either the elements are related by R, so either we have 1 here or 1 in MS. So I hope you can see that this should be the join of the 2 Boolean matrices. So here, join of matrices. Join of matrices. Remember the join operation of Boolean matrices, which says that we look entry by entry, and 1 join 1 is 1, 1 join 0 is still 1, and 0 join 1 is also 1, 0 join 0 is 0. So if we have 0 here and 0 here, this means that AB is not related by R and AB is not related by S, so they should not be related by U because U is the union. Okay, so this is the first new operation we define. Okay, it is the union of 2 relations. Okay, so the union. Now, the second relation we want to introduce is the intersection of 2 relations. So we define the relation I, capital I, by saying that capital I is the intersection of the 2 relations R intersection S. And notice this is a subset. R intersection S is a subset of A cross B because R and S are subsets of R cross B. Now let's see. An element A is related to the relation I to an element B if and only if it is in R and in S. The pair is in R and in S. So this means if and only if A is related to B by R and A is related to B by S. Okay? So the pair AB belongs to this new relation I if and only if the pair belongs to R and belongs to S. So here means the pair AB belongs to R, meaning that A is related to B via the relation R, and also A is related to B via the relation S. So the pair AB belongs to S. Okay, now in terms of Boolean matrices, the matrix representing the relation R intersection S is obtained by taking the meet of the matrix MR meet the matrix MS. Because what does it mean? Who are the elements here? There are two elements are related here. So here we have one, if and only if we have one here and one here. So this means we need, and the only case where we have one when we have one in MR and one in MS is when we use the meet. So this is the meet of matrices, of Boolean matrices. Remember, if we have an entry here 0 meet anything else, we get 0. And this is what we want to say, that they shouldn't be related using the intersection if they are not related either by R or by S. They must be related by both R and S to be related by the intersection. Okay, and the third relation, we will have an example now. Okay, but the third relation is the complement of a relation R. So the complement of a relation R is denoted by CR complement, or if you want RC, and this is that every element will be related here if and only if it's not related in R. Okay, so how we will define this? This will be the set A cross B, because okay, so let me draw the picture first. Suppose this is the set A cross B. This is the set of all pairs. And what is R? R is a relation, it's a subset of A cross B. Now the complement of R is the relation RC. So RC is A cross B minus the set R. So all pairs in A cross B which are not in R. So what does this mean? That a relation, an element A is related by R complement to an element B if and only if A is not related by B. So is not related to B by R. Okay. Now what do you think is the matrix, Boolean matrix representing the complement? It should be obtained from MR by swapping the ones, by changing ones to zeros and zeros to ones. So I hope you can see that this is equal to M of A cross B. What's M? What is the matrix representing this relation A cross B? A cross B is the full relation. Every element is related to the other. So here we have a matrix of whose entries are all ones. We have ones everywhere, minus the matrix MR. So this means if we have 1 here in MR, then 1 minus 1 will be 0. So we will swap 1 to 0. And if we have 0 in MR, which means A is not related to B, then 1 minus 0 is 1. So it will be 1 in MRC, which means the unrelated pair will become related in the complement. Okay, let's take an example on these three ideas: the union, the intersection, and the complement. So suppose we are given two relations, say on the same set. So suppose A is the set containing A, B, and C. We have 3 elements, and MR is the matrix given to us by 1, 0, 1, 1, 0, 0, and 0, 1, 0. So this is the matrix representing the relation R. Okay, and here is the matrix representing the relation S. It's 1, 0, 1, 0, 1, 1, and 1, 0, 0. Okay, so what do we want to compute? Okay, first you can, okay, let me see. We can talk about, so we have 3 elements, A, B, and C, and here we have A, B, and C. And now this is R. R says, so this row represents the element A, B, and C, A, B, and C, and this is A, B, and C, A, B, and C. So notice here R and S are relations on A, which means from A to itself. Now, so from R we know A is related to itself, and A is related to C. So this is A, this is B, and this is C. And from second row we know that B is related to A. Okay. And from the third we know that C is related to B. So we have this, and here we have that A is related to itself. Okay, A is related to C, B is related to B and to C. So it's related to itself and as well to C, and what else? C is related to A. Okay. Now, in terms of sets, then M sub R is what? It is the set. Sorry, not now. This is R, not the matrix. The relation R itself contains 4 pairs. So it contains AA, AC, BA, and CB, right? This is the last one, CB. And S is the relation. What is S? It is from here. We have A is related to A and A is related to C. Okay, what else? We have these two ones. B is related to B and B is related to C. So B is related to B and B is related to C. And finally we have the 5th one, which says C is related to A. Okay, so C is related to A. Now from these R and S we obtain the relation R union S. Okay, so what is R union S? It is AA, AC, BA, CB. Okay, what else do we have? BB, BC, right? And finally CA. So we should expect to have 1, 2, 3, 4, 5, 6, 7 ones in the matrix MR union S. So what is MR union S? It is the join of MR join MS, and this will be a 3 by 3 matrix where we take the one. Okay, so we take the join of the corresponding entries. So here 1 join 1 is 1, and 0 join 0 is 0, 1 join 1 is 1. So we know the first row here is 1, 0, 1. Now in the second row, so look here, 1 join 0 is 1, 0 join 1 is 1, and 0 join 1 is also 1. So here we have 3 ones, 1, 1, and 1. And here we have 1, 1, and 0. Okay, 1, 1, and 0. So we just took the join of the corresponding entries and notice that, so this is A, B, C, A. So this column representing C. Now AA is this one, AC is this one, BA is this one, and then we have CB. Where is CB? It is this one. And BB is this one, BC is this one, and finally CA is this one. So see, this matrix represents this relation. Okay? And similarly, you can compute what's the matrix of R intersection S, which will be the join of, the meet. Okay, let's do it quickly. So what do you expect? Now we are looking for the intersection of R intersection S. So this belongs to the intersection. Here it is, A and C as well. And what else? BA, no, and CB, no. So we only have 2 ones. So notice that R intersection S only has 2 pairs, right? They are AA and AC. AA and AC. And if you want to compute the matrix representing the intersection, then this will be the 3 by 3 matrix, which is the meet of these 2 matrices. So look here. So here we have a 1, 1, 0, 0, 1, and 1 is 1, and the rest, when you take the meet, so look at this, is the meet of 1 and 0 is 0, the meet of 0 and 1 is 0 as well. Here we have a 0, a 0, a 0, and here 1 meets 0 is also 0. So we know that the matrix representing the intersection is so let's put it here. It's 1, 0, 1, and the rest are zeros. So this one represents A is related to A, and this one represents A related to C. Now finally, let's find what's the complement, the matrix representing R complement. So we look at R. So this is the relation R, and now we will consider all arrows possible arrows which are not in R. So I will draw them with green. So we want B to be related to itself. So here I'm computing R complement. So C is related to C, and B is related to C, C is related to A, and what else? A is related to B, and that's it. So the red arrows correspond to RC, and the black arrows, the complement of R, correspond to R. In terms of matrices, we just swap the 1s to 0s and the 0s to 1s. Okay, so in this case, we will get that this will be 0, 1, 0, 0, 1, 1, and 1, 0. Okay. So this is, and check that this is M A cross A. So this is the matrix of all 1s minus M, the matrix of R. Now, so we've seen the union, intersection, and the complement of relations. Now you finally want to see the fourth and last operation, or a new relation from old relations, which is decomposition of relations. So suppose we have relations, we are given the following relations. R, which is a relation from A to B. So it's a subset of A cross B. And we have the relation S from B to C. So it's a subset of B cross C. Then given these two relations, we can define, okay, maybe I can, okay, so this is the set A, this is the set B, and this is the set C. And here we have a element A which is related to an element B via the relation R, and B is related to an element C via the relation S. Then we want to define a relation called decomposition from A to C, and this is called S after R, in a similar way we did to functions. Okay, what is then defined? S composed after R, or composed with R, and this means this is a set, this will be a relation from A to C. Okay, it will be the pairs, all pairs A, C. Okay, so this is an element of A cross C, such that there exists some element B in an intermediate element B in B, such that this A is related to B by R. Okay, so this is B, and the same B is related to C by S. Okay, and notice that this is a subset of A cross C. So this means that S composed with R, or S after R, is a relation from A to C. Again, what is this relation? It is the set of all pairs. A in A, okay, so here is A, and C in C. So we will declare this element is related to this element if and only if we can find an intermediate element B in which A is related to B by R and B is related to C by S. Okay, so let's have an example. Okay, so suppose we have A is the set containing the elements 1, 2, and 3, and so this is the set A. Now we have the set B contains the elements A, B, C, D. So A, B, C, and D. And we have the set C, which contains the elements alpha, beta, and gamma. And we have a relation R from A to B defined as follows. So 1 is related to A and D. 1 is related to A, and it's related to D, and 2 is related to C, okay, and 3 is related to both A and D. It's related to A and related to D. So this is the relation R from A to B. Now we have another relation S from B to C. Okay, how is this relation? A is related to alpha, B is related to alpha as well. Okay, C is related to both beta and gamma, and finally D is related to beta. Okay, so now what we want to do is, from these two relations, we will compute the composition, which is S after R. It will be the relation from A to C, which is given by, so look here, 1 is related to alpha. Why 1 is related to alpha? Again, why? Okay, so look, why this one is related to this alpha? Because there exists an intermediate element which is A here in B, so here it is in green, such that 1 is related to A and A is related to alpha. So we can define, so by definition of decomposition, 1 must be related to alpha. Okay, second, since 1 is related to D and D is related to beta, then 1 is also related to beta, okay, because D is the intermediate element between 1 and beta. And second, we can see that 2 is related to beta and gamma. So 2 is related to beta and 2 is related to gamma because this is the intermediate element, C. Okay. 2 is related to C by R and C is related to beta by S. So we conclude that 2 is related to beta by S composition R. S. Okay, this is the new relation. And similarly to gamma. And finally, what can we check about 3? 3 is related to A and A is related to alpha. So it must be the case that 3 is related to alpha and 3 is related to D and D is related to beta. So 3 is related to beta. Okay, so this is our new relation. Okay, if you want, we can sketch it. So this is 1, 2, 3. This is the set A and this is the set C. This is alpha, beta, gamma, and we know that 1 is related to alpha and 1 is related to beta. 2 is related to beta and gamma. Okay, and what else? And 3 is related to alpha and beta. So this is the relation S composed with R from A to C. Okay. Now when we have a relation, if R is a relation on a set A, okay, remember this means that R is a subset of A cross A, then we want to define the nth power of R. Okay, the nth power of R using decomposition. Okay, so R squared, the second power of R, is simply the composition of R with itself. So it will be a relation from A to A. Now R cubed is the composition of R squared after R. So first apply R and then R squared. Okay, R to the power 4 is R cubed composed with R, and so on. So in general, R to the n plus 1 power is R to the nth power composed with R. So here you imagine this is A, and A. And first we have the relation R from A to A, and from A to A we have R to the n. You compose these two and we get the relation R to the power n plus 1. Okay, this is how we define the nth power. Okay, now let me finish this session by saying a lemma, which I will leave it for you to check, that if R is a relation from A to B and S is a relation from B to C, then the matrix of S composed with R, so first apply R and then, okay, so this is the picture. A, B, C, we have a relation R here and the relation S here, and we define the composition S after R, so first apply R and then S. Then this matrix can be obtained from the matrix representing R and the matrix representing S by the Boolean product. Okay, so this is the Boolean product. Okay, so you can check here. Okay, so you can check it here. Write MR. So from R. Okay, so this is R, right? The blue arrows are R. We can write the matrix MR representing this relation, and from the red arrows you can get MS, And then this matrix representing this relation, sorry, S composed with R, will be equal to the matrix representing R Boolean product, the matrix representing S. You should remember what is the Boolean product of two Boolean matrices. The entries in the Boolean product are equal to the join of the meets of the corresponding ith row and jth column.